In this video, we will finish our study of Chapter 8. We will be testing a claim about a population mean. Testing a claim about a population mean is a very important method in this book. We will study only part 1 of this section, which deals with the more realistic and commonly used case where our population standard deviation is not known. We will not be going through part 2 at all because it's so rare. So we will be using the case where we do not know the population standard deviation. Our objective in this section is to use the methods of formal hypothesis testing to test the claim about a population mean mu. Just like in the previous section, we want to have a common list of notation, where n is our sample size, x bar is our sample mean, s is our sample standard deviation, and mu, or mu sub x bar, is our population mean. And again, just like previously, there are a list of requirements. However, for our examples, they will always be satisfied. So we do not need to worry about them. What is different about the population mean is that we cannot use the standard deviation z. What we have to do when we create our test statistic is use the student t distribution, which is going to be listed here, where t is equal to x bar minus mu sub x bar divided by s over root n. And again, we have the same two methods. We can use the p-value or the critical values method. We will restrict ourselves to the critical values because in this case, we cannot really use the p-values method. So we will forego that and really just stick to the critical values method. Let's refamiliarize ourselves with the student t distribution. There are a few important properties when talking about the student t distribution, and that is that the student t distribution is different for different sample sizes. That is why we had to deal with the degrees of freedom. The student t distribution has a general bell shape, but it is wider and flatter to reflect the difference when we use different values of s and different values for our sample size. Just like the standard distribution, our t distribution has a mean of 0. And as the sample size n gets larger, the student t distribution will get to approximate the standard normal distribution. Let's look at the first of two examples. An author obtained times of sleep for randomly selected adults included in a national health and nutrition examination study, and the times or hours are listed below. Here, we need to compute the sample mean and the sample standard deviation, which is computed for us. For these 12 items, the sample mean x bar is 6.8333 repeating, and the standard deviation s is 1.99240984. What we will do, again, is not use the p-value method. We will use the critical value method with a significance level here of 0.5 to test the claim that the mean amount of sleep is less than 7 hours. So let's get to it. So our claim is that the mean amount of hours of adult sleep is less than 7 hours. So again, our original claim is the mean is less than 7. And so again, what we want to do is we want to take our claim of the mean being less than 7 and convert it to its opposite, which is the mean being greater than or equal to 7. Our null hypothesis, h sub 0, will always be the version of this with equality. So the null hypothesis will be the mean is equal to 7. And the alternative hypothesis will be either one of these two, which does not contain equality. And here, this one does not contain equality. So our alternative hypothesis is that the mean amount of sleep is less than 7 hours. To continue, we need to recall that our significance level, alpha, is 0.05. And because we're testing a claim about a population mean, we need to use the t distribution, where the formula is described here. And if we recall the values, n was 12, x bar was computed, that was 6.83 repeating, which will just lead to 3 decimal places. The population mean was 7, and the sample standard deviation was 1.992. And so we can compute our test statistic in terms of the t-distribution in this case. 6.833 minus 7 divided by 1.992 all over the square root of 12. And if I compute this, I'm going to get negative 0.290. That is our test statistic. So to finish testing our claim, we want to draw our distribution, our t-distribution, which again has a mean of 0. And because my alternative hypothesis, my original claim, was that p is less than 7, this is going to be a left-tailed test. So I want all the significance of 0.05 to be the area to the left, which means I have to be over here. So my region I'm drawing has that whole alpha value of 0.05 to the left. This value of t, I'm going to have to read off the chart. And again, this is going to be the area in one tail, and I'm going to want to have the degrees of freedom, again, to be n minus 1, which in this case is 12 minus 1, which is 11. So let's look at our t distribution chart. Here is our t distribution critical values chart. And again, because I have a left-tailed test, I want the area in that one tail to be my 0.05. And again, I have my degrees of freedom being 11. So my critical value is going to be where they meet, which is 1.796. However, this is a positive value. But if we look at our chart, we clearly have a negative critical value because it's to the left of our mean. So all we do is just make this number negative, right? We're okay to do that. So that critical value we have that marks off that critical region is going to be negative 1.796. So now we know our critical value that marks off our critical region is negative 1.796. If we look at our test statistic, it's negative 0.29, which has to fall somewhere in between our critical value t and our mean of 0. So this falls outside the critical region. So what is our main conclusion from this? Go. What we can conclude is because our test statistic falls outside of the critical region, we actually have to fail to reject the null hypothesis. We fail to reject it and say there is not enough evidence to support our alternative hypothesis. That is how we will conclude an example like this. Let's look at our last example. Here, we're going to revisit the idea of body temperature, where we have 106 people in this study. We found a sample mean for their body temperatures to be 98.2 degrees Fahrenheit with a sample standard deviation of 0.62. And we want to use a 0.05 significance level to test the claim that the population mean is 98.6. This example is going to be different because our claim symbolically is that the mean is equal to 98.6. And again, when building the alternative and null hypothesis, we take our claim of our mean being equal to 98.6, and I want to convert it to the complete opposite. Well, the opposite of equality is not equals 98.6. So our null hypothesis will always be the claim equaling our value. And again, out of the original claim and the claim not containing equality, our alternative hypothesis is the one that avoids equality. So in this case, our alternative hypothesis would be mu is not equal to 98.6. This is our first example of what we call the two-tailed test. Why is this a two-tailed test? Well, if our mean cannot equal 98.6, it could be less than 98.6, or mu could be greater than 98.6. In this case, we don't know which one is true, so we have to include both of them. And in this case, our alpha level of 0.05 has to be split into alpha over 2 to the left being 0.025, or alpha over 2 to the right, again, being 0.025. So let's compute our test statistic having a significance level of 0.05. Again, we're computing the test statistic t in this case, being x bar minus mu, all divided by s over the square root of n. And if we recall from our example, we have 106 people in our sample. The sample mean is 98.2. Our population mean claim is 98.6. And our sample standard deviation is 0.62. So we can compute our test statistic, 98.2 minus 98.6, divided by 0.62 over the square root of 106. And if I compute this and round to 2 decimal places, I get negative 6.64 as our test statistic. And again, this case is unusual because our alternative hypothesis is that the mean is not equal to 98.6. And as stated, this will yield a two-tailed test. So we take our whole significance level of alpha being 0.05 and we split it in between two tails. So there's a t-value to the left and an equivalent negative t-value to the right. Here, where our significance level is 0.25 and 0.025 as well, right? This splitting of alpha should be very similar to the confidence intervals we did in Chapter 7. So what we have to do now is look at our student t-distribution chart and find a t-value, a critical t-value, with an area to the left of 0.25 in a single tail, having the degrees of freedom, again being n minus 1, which in this case is 106 minus 1, which is 105. We have our student t distribution for the critical t-values. Again, I want an area in one of those two tails to be 0.025. So I'm looking down this middle column. And what I want to notice is as I scroll down, my degrees of freedom are starting to get further and further away. And if I look, I do not have 105 exactly. What we'll do is we'll look at the closest degrees of freedom we have on the chart to what our degree of freedom is, which is 100. If I look at the column or row of 100 and look at where they intersect, I look at my t-score there to be 1.984. However, because we have a two-tailed test, we should have two t-values, one of them being 1.984 and the other one being the equivalent negative value of negative 1.984. And so now we have the values that mark off our critical region. Our critical region, again, is the two tails, one to the left of one to the right, marked off by negative 1.984 and 1.984 respectively. And we look at our test statistic, which we computed to be negative 6.64, and say, where will this fall on my chart? And we can clearly see that negative 6 is going to be pretty far to the left. So it will be contained in our critical region. So our final conclusion, because the test statistic is inside the critical region, we can reject the null hypothesis, H sub 0. There is sufficient evidence to support the alternative hypothesis that the internal body temperature of the average adult is not 98.6 degrees. Hopefully you found this helpful. If you have any questions, feel free to send me an email. If not, I'll speak to you next time.